We'll start the session exactly on time this morning. First speaker will be Karlheinz Groechenig from the University of Vienna. So the full session is Austro-German this morning. So the first representative will be Charlie, that he will be speaking about T-design curve.
Well, good morning. I'd like to thank the organizers for inviting me. The Newton Institute is a great place, so I'm really happy to be here. I have given this talk a few times, so some of you may have heard this already. I apologize. But the topic fits to this conference. It's multivariate. It's, what else? What else? There's some discretization and some reconstruction. So it fits. So we have heard several times during this week already that measurements are expensive. I would say measurement devices may be expensive, and perhaps the first idea to replace many sensors or measurement devices by one was proposed many years ago by Martin Wetterli. He proposed to, instead of using many sensors, so this would be the many points that you see here, by a single sensor, but moving that sensor along a curve and sample a physical quantity in this way. So that leads to the concept of mobile sampling. Replace many expensive sensors by a single one, but sample a stationary field along a curve. Another example where this might be useful is from my colleagues at the Acoustics Research Institute in Vienna. So I copied this. So they have a room, soundproof room, and many speakers, and in psychoacoustics experiments, they try to move the sound and test and measure your reaction. So you see there are many speakers here, and well, maybe it's cheaper to choose just one speaker and move that one speaker around. So that's something where we might actually have to say something. So mobile sampling and the manifold is the sphere. So let me go to the precise setup and definitions. So mobile sampling, we move along curves, and in our case, curves on the sphere. So a curve is a map from an interval into the D sphere, so set of all points of distance 1 to the origin. And by a curve, I will understand a closed curve, should be piecewise smooth, and finitely many self-intersections. Now when we do approximation theory, we approximate by polynomials, so the underlying scale of spaces will be the space pi sub t. Those are the algebraic polynomials of degree t, and since we are on the D sphere, we have d plus 1 variables. So we move along a curve, so the underlying object or measurement is the line integral of a function f along that curve. So to recall, you evaluate the function along the curve, multiply by the speed, and then integrate. The arc length is the integral of the constant function 1 along the curve. And then the main definition that we're going to deal with is the concept of a T-design curve. So gamma is a T-design curve if the normalized line integral, so line integral of f along the curve divided by the length of the curve equals the integral of f over the full sphere with surface measure. And what's important is the quantifier. That should be true for all algebraic polynomials of degree t. So averaged or normalized line integral equals integral for all polynomials of degree t. So you could say this is an exact integration rule for polynomials of degree at most t. So as far as I can tell, this is a new definition, but of course there's a point of reference, and this would be the spherical designs or t designs. In that case, you deal with a set of points, and so a finite set would be a spherical t design, or I would say t design points, if the averaged value, function value, coincides with the integral over the sphere for all polynomials of degree t. So t design always refers to the degree of the polynomials where I have exactness. So this plays an important role in quadrature rules on the sphere. I think one of the earliest references, a paper by Goethals, Delzart, Seidel. Such point sets exist. So that was established in the 80s and 90s. What's important is, okay, question is, how many points do you need? And one of the important conjectures was the cardinality of a t design curve is of the order t to the d. Well, the rule of thumb is t to the d is the order of the dimension of the space of algebraic polynomials. So there is a huge literature on t design points, construction of t design points, tables, and the outstanding problem was the asymptotic, the construction of asymptotically of t designs with asymptotical optimal cardinality, and that was solved only 11 years ago by a famous paper by Bondarenko, Radchenko, and Vyazovska. They solved this conjecture. There exist t design points of the correct order of cardinality. So this would be the reference and the comparison. So just to give you an idea how such t design curves might look like, I show you some ad hoc constructions. Well, you have to start with some curves. So I should say this is joint work with Martin Ehler from the University of Vienna, and part of the numerics is by Clemens Karner. So Martin just checked curves. What kinds of curves could he try? And this is one of them. Doesn't matter how it looks like, but there is a parameter a, and if you fit that parameter, then for a particular, where there are two values of a, 0.78 and 1 minus 0.78, for which the corresponding curve is a two design curves. So moving along that curve, computing the normalized line integral, you get the correct integration for all quadratic polynomials. There's a relation to tight frames, but I don't go into that. So this is a nice curve, actually smooth, no self-intersections. It looks like the seam of a tennis ball. An idea that somehow looked promising, you start with control points, and then you so in this case we have 4 points. There's a parameter involved, and you connect the points along geodesic arcs, so arcs along great circles, and check whether that corresponding curve, now it has, well, it's not everywhere differentiable, whether that's a t-design curve. And there are two curves. For a certain parameter of a, the 4 points form a simplex, a regular tetrahedron, and so the vertices form two design points. So the average at these points gives you exact quadrature for quadratic polynomials. However, if you look at the corresponding curve connecting these vertices, it's not a two design curve. So no exact quadrature if you move along the curve. Now, the idea is, well, we deform these points. Well, there's only one parameter involved. We deform these points, follow the same recipe, connect the points along geodesic arcs, and there's a particular value, it's different from this one here, where you obtain a 2 design curve. Well, these are computations, estimates, mean value theorem. It's elementary, but requires some work. So you find a value of A, in other words, a configuration of 4 points, where you get the 2 design curve after connecting these points. But the moral is it's different from connecting points to a curve. So here is another example with 6 points. So for a certain, and a parameter A, so for a certain value of A, you get an octahedron. So the points, the vertices form 3 design points, but when you connect, you don't get anything. If you distort the point set and connect, then you get the 3 design curve. So there seems to be a difference. Well, this is a new result, not even written up, not even typed yet. So the idea of taking T-design points and connecting them along geodesic arc at least gives you something. It gives you Marcinkiewicz-Zygmunt inequalities. So if you take a set of sufficiently dense T-design points and connect them suitably, then to get a short curve, then you get the curve of length t to the d minus 1. I'll explain in a moment why t to the d minus 1, such that the averaged line integral, so here in the 2 norm, the 2 norm is equivalent to the 2 norm of f over the full sphere for all polynomials of degree t. So you get, so by connecting T-design points along arcs, you don't get curves, you don't get exact quadrature, but you get Marcinkiewicz-Zygmunt inequalities along curves. So you get something, but not exact quadrature. So that's, I would say, sufficient for many purposes except quadrature. So explicit construction of T-design curves is not that. So can I do this? Let's see. Well, maybe not. So it's not that easy, and in numerical analysis, many people have actually put up websites and lists with T-design points up to degree 200, 300. There are one by Manuel Greff and one by Womersley. You can check that. So this is, even explicit examples it's I think, difficult problem, but it's useful. So the examples I showed you, well, they are toy examples, but that's all we know at this time. So now let's go to a bit of theory and the results that we have been able to obtain. So you can always prove something. I think that would be my philosophy. But in the end, you want to know what you have proved and how useful or good it is. So the first thing is, what is possible when you try to construct a T-design curve? And so here is a necessary condition. If you have a T-design curve, in other words, a quadrature rule for a line integral for polynomials of degree t, then you have a lower bound for the length. And that lower bound is of order t to the d minus 1. If you compare with T-design points, there you have the cardinality of a set of T-design points is t to the d. Now this is, well, as a rule of thumb, that's easy because the dimension of the space of polynomials of degree t is it's the sum of 2 binomial coefficients, so it's of the order t to the d. So that's easy to guess. This is less obvious, but what you notice is you lose one power here. So there is a lower bound for the length of the curve. And at some point you might ask, well, why do we need closed curves? I will explain that later when we go through a proof idea. So the best you can hope for a t-design curve is a curve of length of the order t to the d minus 1. Can we do that? So the first result would be t-design curves on the 2-sphere. So that's something we can actually visualize. Sphere in R3. And on the 2-sphere, there exists, for every t, there exist t-design curves of length of the order t. So bounded above and below by a constant times t. And if you compare for d equals 2, the length of the curve should be roughly proportional to the degree of t. So such curves exist, and that would correspond to the solution of the Correvar-Meyers conjecture that you have spherical t-design points of order t to the d. So in that dimension 2, the existence, you can take it for granted. Next question is, of course, higher dimensions. And there, all we can show is the existence of t-design curves. So for every t, there exist curves that satisfy the quadrature rule, but the length is bounded by degree to the d times d minus 1/2, so roughly t to the d squared. That's actually the state of the art in t-design points before the resolution of the big conjecture. So that conjecture was open for 20 years, and before that it was, you need t to the d squared, and before that it was t to the d cubed. So this is basically at that level. But at least the existence of such t-design curves is established. So these are the 3 results that I want to talk about in a bit more detail and show you some of the arguments. We don't start from scratch. We actually use the fundamental result. There exist t-design points of asymptotically optimal cardinality. So we use, this is a deep result. We use that result and base our construction on that. We use some usual standard harmonic analysis on the sphere, spherical harmonics, a lemma that often looks like what is called the mean value property for harmonic functions, but seems to be related but different. And there's some combinatorial argument. So I won't go into arguments for the lower bound. Philippe Jamin presented many arguments in the context of what's called the sieve inequalities that's basically the arguments of that type. I want to show you some of the arguments for the existence. And for the existence, I do that on the sphere because that's less, on the 2-sphere because that's less technical. And an important ingredient is a formula by Zamko. And okay, so let's set that up. So we're on the sphere. So we have a distance on the sphere. Basically, the distance between 2 points is we measure that by the angle. And then you have spherical caps. So all points at distance r from a point x, so spherical caps. On the 2-sphere, the boundary of a spherical cap is a Euclidean circle. Okay, we'll see a picture. So that's one thing we need. And the second thing is a bit more information about the space of algebraic polynomials. there is a decomposition of polynomials of degree t, an orthogonal decomposition into invariant subspaces. And so invariant subspace sub k, there are three possible descriptions. One is this space H sub k consists of all homogeneous harmonic polynomials of degree k restricted to the two-sphere. So polynomials, they satisfy Laplace equation and they are homogeneous and degree k. That's one description. Another description is they are eigenfunctions of the Laplace Beltrami operator on the sphere corresponding to the eigenvalue k times k plus 1. So these are abstract descriptions. And the third one, at least on the two-sphere, is nice when you want to do computations. It's the span of the spherical polynomials. So this is some general Legendre polynomial at cosine theta times exponential, and you have a nice description in terms of spherical coordinates. Okay, so here is Zamko's formula. So as I said, the boundary of a spherical cap on the sphere is a circle. So the boundary is a circle. You can give it an orientation, it doesn't matter. And then the normalist line integral of a polynomial in one of these invariant subspaces is proportional to the polynomial evaluated at the center of the spherical cap. And the constant here depends on the radius of the spherical cap and depends on the number, the label of that eigenspace. But this formula is independent of a particular polynomial, and it's independent of the center. So so normalized line integral is related to point evaluation. So why is that important? This formula connects line integrals to point evaluations. And perhaps here is an illustration. So here we have a spherical cap of some radius, and if you calculate the line integral on the boundary along the circle, then you get a multiple of the value of the polynomial at the center. On the two-sphere, the proof is not difficult. You rotate so that the spherical cap is centered at the North Pole. Then you look at, geographical latitudes. So you integrate along phi with r being fixed, and you do the computation, and you get the formula. So this is an elementary computation when you use this particular description of these eigenspaces. So Zamko's formula connects line integrals along circles to point evaluations. And now we combine that with t-design points. So we take t-design points, so t, and we know that there are t-design points of cardinality t squared. And well, first of all, cardinality t squared, and the property is that the average function value equals the integral over the sphere for all polynomials of degree t. Now this is an orthogonal decomposition. If you take the constant 1 here, then you have 1 equals 1. Okay, that's correct. If you take something orthogonal to the constant, then it's in one of these spaces. And well, when you're orthogonal to the constant 1, then this line integral is 0, and the average is 0. Okay, so let's multiply by the constant from Zamko's lemma. If you take a polynomial orthogonal to the constant function in one of these invariant subspaces of polynomials, then you get 0 here. So this average is equal to 0. And now you have this constant times function value, and you read Zamko's lemma this way. So constant times function value is a line integral along a circle. So you plug that in. So point evaluation times this constant is equal to the averaged line integral along the circle. So here we have gained something, because on this side we have a sum of line integrals, or you could say it's a line integral along a cycle, and on this side we have, well, some average point evaluation, and if we read this way, we get that sort of integral along a cycle for a polynomial in one of these invariant subspaces is equal to 0, is equal to the full surface integral. So let me summarize that. We define a cycle, so that's the union of these circles. We can choose an arbitrary orientation on the circle, doesn't matter. Now, this gamma r sub t is a union of closed curves, is a cycle. Its length is the radius of each circle times the number of such circles. So it's r times the cardinality of such a t design points. And well, for every f for every f in this invariant subspace, you get 0 here. So if you take a sum, you get 0 on this side. For the constant, you get 1 here. And so what I showed you before shows that the integral, so the normalized integral along this cycle is equal to the integral over the sphere. So you have exactness for for polynomials of degree t. What's missing? Well, what's missing is single curve. And here I finally should explain why we insist in closed curve. There's one free parameter left, the radius of the spherical caps. So if, what's happening? So if you choose the radius small, then these spherical caps don't intersect, and you have many disjoint circles. So that would amount of having the same number of sensors as in the original problem. No use. And of course, if you choose the radius small, then you can make the arc length of that cycle arbitrarily small. Well, that's not what we want. We want a single sensor. So now we start increasing the radius of these spherical caps. So here we have very small arc length of the cycle. We increase the radius. Well, okay, nothing happens. We increase the radius until the spherical caps cover the sphere. And when they cover, then the spherical caps must overlap. That means the boundaries intersect. So, and we take the smallest radius where we get the covering as the radius to work with. So we choose that radius, that's still a free parameter, so that the corresponding spherical caps cover the sphere. So we choose the covering radius, and then you can check or just cite that the covering radius for t-design points is of the order 1 over t, 1 over the degree of the polynomials. So as a consequence, the length for this particular radius, the length of the cycle is the number of points, so t squared times covering radius, it's 1 over t, is t. Fine, that's what we announced. That's sort of the lower, that's a necessary condition on the length of a t-design curve. When you go back at this image, okay, so we still have a union of circles, but the circles intersect. Now, the final step, we have to construct a closed curve from these circles. And okay, here's, so from this union of circles that intersect, we want to construct a single closed curve. And the way to do that is a combinatorial argument. So we associate a directed graph to this union of circles. The points of intersection will be the vertices of this graph, and the edges are the connecting arcs between these circles. So in this way, and if you choose an orientation, you get a directed graph. And now the question is, can I design a path on this graph that's closed? So I start here, I want to go back to this point, and so that I run through every edge exactly once. So I didn't know any graph theory before, but I found out this is on page 5 on every introductory book on graph theory, and it's known as the Königsberg-Euler's problem of the bridges in Königsberg. So you know what to test. The number of ingoing vertices must equal to the number of outgoing vertices, and by this construction, that's the case. You have an ingoing vertex, and since the point of intersection is on a circle, you have an outgoing edge. And if you have, yeah, okay, so number of ingoing edges is number of outgoing edges at each vertex, and that implies that you have an Euler path, so a path on that graph that traverses every edge exactly once, and that is closed, so you return. So in other words, the graph is strongly connected, and you have an Euler cycle that implies that you can arrange these arcs on this union of circles into a closed curve. Well, this closed curve is obviously piecewise smooth, contains of geodesic arcs. It has finitely many self-intersections, and then we are...
Why are they geodesic? They're not geodesic.
Oh, sorry, they're circles. Yes, they're not geodesic. Thank you. Okay, so that is the end of the proof idea in dimension 2. Yeah, okay, so I think that, but the idea is we don't use arcs connecting the t-design points, but with circles around the t-design points. I think that was the main insight we obtained. The curves don't look that nice, but at least we have existence. So in higher dimensions, well, the observation is if you look at the spherical cap, then the boundary of a spherical cap is actually a sphere of is isomorphic to a sphere, but a d-1 sphere. So now you argue by induction. Suppose you have a t-design curve in a d-1 sphere. You can embed that t-design curve into the boundary of a spherical cap. There you have a version of Zamko's lemma, and in this case you can relate normalized line integrals to point evaluations, and then you use induction. That has turned out to be rather technical, but the idea is to use induction, and in that induction process you lose something, and all you get is order t to the d squared. So in higher dimensions we get existence of t-design curves. So let's see, I have 5 minutes, right? And not too many slides. So, so far I've been concerned with quadrature rules, but from quadrature you can go to reconstruction and you can go back. So just to show you how you could reconstruct a polynomial from its values on a 2 design curve. So suppose gamma is a 2 design curve, then here's an explicit reconstruction formula for a polynomial of degree t from its values on a 2 design curve. So basically take the inner product with the reproducing kernel. The reproducing kernel is a polynomial of degree t, so the product is a polynomial of degree 2t, and so the average line integral is equal to the inner product of f with the reproducing kernel is equal to the point evaluation. So this would be, in principle, a reconstruction of a polynomial of degree t from its values on a 2t design curve. So that's basically what I wanted to tell you. We have a lot of work to do. Not clear how much we can do. The main open problem is T design curves in higher dimensional spheres of the correct length. One could try to use submanifolds. At least for mathematicians, it would be a natural generalization. I don't quite see a good motivation from applications, but so what? You might want to construct nicer curves. If you recall the seams of a tennis ball. That's a smooth curve, no self-intersection. The construction gives you piecewise smooth with many self-intersections. We have no systematic explicit constructions. That may be very hard. It's very hard already for points. There's one point that looks innocent. You might want to construct T-design curves on more general compact Riemannian manifolds. We have some examples of that for the torus, for some Grassmannians. But there is a good point to do that, and now let me check. Very good. So here you see I think that's a 5 design curve on this side. Okay, and what you see here is the project. So every point on this curve corresponds to so at every point you have a tangent plane. Okay, and you have on this side, so you have a point cloud in R3, and you project its shadow to a tangent plane given by this parameter. So first of all, you want to show, so this is a 5 design curve. And now if you move, along this curve, you see projections from under different angles, and you get a pretty good idea, so a lower dimensional portrait of that point cloud. Apparently it's two isolated clouds. So here we have projection from R3 to R2, but if you generalize, you have, say, R100, and you want projections into R3, then basically you parameterize the subspaces by, say, Grassmannian, and you want to, say, move through the Grassmannian manifold in such a way that you cover as many directions as possible. So for that, you probably don't need T-design curves, but at least dense enough curves or Marcinkiewicz-Zygmunt curves. And so I think that the transition to other manifolds has some value for applications. I have 12 seconds, and I can say thank you for a few times. Thanks.
have some time for questions. Are you?
So that's all related to discrepancy usually, right? Also for points at least, you have the discrepancy related problem. And you know that there is some energy that is maximized by these points. Do you know if your curves also kind of are maximizers of a specific type of energy?
Let's see, the honest answer is I don't know anything beyond what I told you. Let's see, if let's see, essentially whatever you can do for points, you have to ask for t-design curves. That's legitimate, but we haven't done that yet. Well, we have done that construct. T-design curves is actually probably the hardest question to ask because the exact quadrature is such a rigid definition that, well, that's probably the hardest question to deal with. When you go to Marcinkiewicz-Zygmunt, so inequalities, those are easier to construct, and we have done that. There's a connection to tight continuous frames, two designs. Yeah, it's a legitimate question. I have no answer.
Was another question at the back?
So you have this, you can go from t-designs to t-curves. Do you think you can go from t-curves to discretizing a t-curve?
You can discretize. You will get Marcinkiewicz-Zygmunt inequalities, but so sampling on a t-design curve and to hope that you get t-design points, I think it's hopeless. There may be. That's why I showed you the two examples in the beginning. From points, connecting them, you don't get t-design curves, and the other way around, we don't know, but it's unlikely.
Okay, and I think same questions then. So let's take a 2.5-minute break while the next speaker sets up, and if you need to.